Well, hello again. In our next talk about conditional probability, we're going to delve into the idea of false positives and false negatives. We'll revisit these in inferential statistics when we call them type 1 errors and type 2 errors. But this is a good introduction to that idea. And to be perfectly honest, this problem is the reason I teach probability. If I can get you to understand this situation, then I can feel good about what we're doing in this course. This is why we do it, right? This is a common situation that occurs every day in the medical world. It's certainly occurring now, right? This whole idea of drug testing, right? And antibody testing, right? We know a certain percentage of the population has a disease, takes a drug, does something. We just don't know who. You know, the metaphor I like to use is you've got 100,000 people in a stadium, right? And you know 5,000 of them are sick. You just don't know which 5,000. So you say, okay, well, we'll give them a test. But is the test 100% accurate? And if it's not 100% accurate, what does that mean? Does that mean you're going to have some people who are sick who get a negative test and some people who are not sick who get a positive test? And those are called specificity and sensitivity, right? We have words for those. I'm not so much interested that you know what those words mean, although they are kind of helpful to drop at your next cocktail party. But this is the idea. False positives, false negatives, and conditional probability, because we have the initial condition of what we call the prevalence of the disease. Let's take a look at this problem. A certain disease is randomly found in 1% of the population. So we're going to deal with 1% of the population. Now, we know that it's 1%. We just don't know who. Again, visualize your football stadium, 100,000 people. 1% is 1,000. There's 1,000 people sitting out there who have the disease. We just don't know who they are. Now, here's what we do know. A clinical test has 98% sensitivity. So what does that mean? That means it identifies people who have the disease. So if you have the disease, there's a 98% chance you're going to test positive. What about the other 2%? The test has 96% specificity. Okay, what does that mean? That means if you don't have the disease, you'll test negative. What about the other 4%? We're going to answer those two questions today. And we have these 4 probabilities. So we want to know what's the probability you have the disease if you test positive, which is a little bit different than saying 98%. What's the probability you don't have the disease given a negative test? What's the probability that you don't have the disease given a positive test? And what's the probability that you have the disease given a negative test? So every time you see that given conditional probability, that's right, you're learning. This type of problem lends itself very well to a probability tree. And I'm going to show you a little bit different approach to this. And you can thank Gerd Gergerenzer in the book, The Number Sense, for this analysis. But I think this will help you see it. The number I'm going to use is 100,000 again. Okay? So I think we can use 100,000 here. Let's see, 98%, 96%. I think I'm going to go with, we can go with 100,000. So let's see how this works. So here's our 100,000 people in the stadium. I hope you can see that. Now, what do we know about those 100,000? We know that 1% have the disease. So there's 1,000. That must mean then that 99,000 do not have the disease. Does everybody agree with that? And do you understand that? Now, this is how we start. So, and again, here's the idea. The idea is you probably don't have the disease. So think about that when you go to get tested. You probably don't have the disease. That's why we often say, wait until you're a certain age to go get a test, right? We don't send 16-year-olds for a colonoscopy. Why? Because there's likely nothing wrong based on your age. But that was 16. When you're 56, yeah, there might be something wrong because the prevalence is so much higher. Remember that word. Okay, so here we go. 100,000 people, 1,000 have the disease, 99,000 don't. Now, what do we know? We know that we're 98% sensitive. That means if you have the disease, this will identify you 98% of the time. So we go down here, 980. These people have the disease, okay? And they're correctly diagnosed, all right? Now, we call this a true positive. Does that make sense to you? They are truly positive. Scooch this over just a little bit. So those are our true positives. Now, what does that mean about the other 20 people? So think about those 20. They have the disease, but the test is only 98% accurate. So they come out here with a false negative. So in other words, they're walking around thinking, I don't have the disease. But they really do. Because the clinical test is not 100% accurate. Okay, now let's talk about the 99,000 that don't have the disease. And this is where the newspaper articles get written, right? You hear, maybe you've heard about false positives. Right? Every time an athlete fails a steroid test, they say it's a false positive, right? So we're going to take that 99,000 and I'm going to multiply that by 0.96 because the test is 96% accurate. And when I do that, I get 95040. Okay, so what does that mean? That means 95040. These are going to be our true negatives. Okay? That's great. And that's a pretty good chance you're going to get a true negative if you're negative, but not everybody is. So what happens here to the other, 3,960 people? Well, think about that. They don't have the disease, but the test is only 96% accurate if you don't have the disease. So that must mean that these come back positive, but they don't have the disease. And those are your false positives. And that is your probability tree. And I think based on that probability tree, we can answer those 4 questions. Let's see how this works. All right. I'm going to duck down low here. Maybe I'll sit on this side so you can kind of see the numbers. There we go. Okay, so what's the probability that they have the disease given a positive test? Okay, well, it should be pretty high, right? I mean, if you have a positive test, shouldn't you most likely have the disease? Well, think about it. No, because most of the people don't have the disease. And the small percentage of the false positives of that group are going to be way more than the true positives of the tiny percentage of people that do have the disease. This is where you have to trust the mathematics more than your intuition. All right. Probability you have the disease given a positive test. Well, there's 980 people who have the disease. What's our denominator? Our denominator are the positive tests. So there's 980 positive tests for that group, but there's another 3,960 positive tests that are false. And that's how this works. Okay? When we do this, this comes out actually to be 19.84%. And that's your false positive. So, I mean, this is the idea, right? This is why people cry false positive when that test comes up. Now, this is not necessarily true for everything. And in fact, when you talk about things like HIV, when that test comes back positive, they do another test to make sure. But let's just be clear here. Given a positive test, there's only about 20% of the people that are actually positive. All right, let's go the other way, the negatives now. Well, the negatives are going to be intuitive because most of the people don't have the disease. So given a negative test, let's think about the denominator first. The negative test denominator is 95040 plus another 20. And the numerator is 95040. So again, the false negatives are so low. Why? Because most of the people don't have the disease to start with. And you see, that's the idea. You could easily say, well, I'm not going to go get tested because I probably don't have the disease. And you're right, right? And so that's what we're talking about here. This actually comes out to be 99.98%. So when you're talking about sensitivity, and that should make sense to you, right? Given a negative test, what's the probability you don't have the disease? Well, it's going to be pretty high. Why? Because most of the tests are negative. We're not talking about a disease that's overtaken the population, right? We're talking about a handful of players that use steroids or a handful of people that have the flu, right? And so that's what this is about. Okay, so let's now talk about the next two. And these are the big ones for us. What's the probability you don't have the disease, but you have a positive test? Okay, so let's go back over here. The denominator is the same as it was in the first one. Given the positive test, so we're here, 980 plus 3960. That's our denominator. Now, what's the probability you don't have the disease given the positive test? So, that's this number here, 3960. And when we divide this out, right, when we add another 980 into the bottom, this is about an 80.16% chance. Okay, now, let's just think about that for a second, okay? Given a positive test, there's about an 80% chance you don't have the disease. Now, look at the complement between the first one and the third one. The probability you have the disease given a positive test and the probability you don't have the disease given a positive test. Yeah, those are complements. And do you think you can answer the last one without doing any work? Yeah, it's going to be the complement of 99.98%. Okay, these are called the false positives. And these are going to be your false negative. So what's the probability that you have the disease given a negative test, the false negative? And again, this is going to be all of your negative tests. So what's our denominator here? Think about that. 20 plus 95040. And the numerator is 95040. So here, and that's going to come out to, as you would guess, 0.02%. So in this case, right, the false negative rate's pretty low. There are very few people walking around out there that have the disease thinking that they don't. But the false positive rate is really high. And the false positive rate both of them depend on that rate. What did we call it earlier? I told you to remember the word prevalence, right? The disease is randomly found in 1% of the population, all right? So let's take a look at this probability tree again. 100,000 people, 1,000 are sick, 99,000 aren't. The disease is pretty good, but it's not 100% accurate. So of these 1,000, yeah, most of them are gonna test positive. But the tiny bit will test negative. Of these, most are gonna test negative, of course, but a tiny, maybe not so tiny bit test positive. But here's the deal. Because there are so many negative people, right? The false positives are gonna outweigh the false negatives. And then this is how the probabilities work. Okay, so think about this the next time you're dealing with false positives, false negatives, and drug testing. Thanks, and enjoy your conditional probabilities.